Welcome to the first webinar of 2025. Someone has there's a bit of an echo. Oh, but I switched my. Okay, it's better now. Yeah, okay, there is no echo now. Perfect. So, and our first speaker is Graeme. Yeah, Graeme is a postdoc in Stellenbosch, and we will speak about some of his exciting results of last year. Yeah, Graeme, are you ready?
Yes.
Yeah,
okay.
Perfect. Then you can. Sorry, I've forgotten the title of your talk. And in the rush, I didn't bring it with me. Sorry. Please, Graeme, you're most welcome.
Okay, yeah, thank you, Francesco, and thanks for everybody that's joining us in person and online. So let me just share my slides. It's probably a good place to start. Okay, just to check that everybody can see my slides online and you can see my cursor.
Yeah.
Okay. So yeah, so the the title of my of this webinar will be non-equilibrium quantum heat transport between structures and environments. So that's maybe a little bit overly technical title. So this talk will kind of more broadly be on kind of open quantum systems theory and quantum thermodynamics. So for maybe those of you who aren't so familiar with these topics, I'll try to give a kind of more slow kind of pedagogical introduction before I start talking about the more kind of technical aspects of this area. So just to mention as well, the more kind of the later parts of the talk are more specifically on a paper that was published last year in News Journal of Physics in collaboration with Professor Francesco Prescioni. Okay, and also just to mention that ideally I'd like to make this kind of as open as possible. So if people online have any questions, then I think you know, feel free to just interrupt me and unmute yourself and ask questions. Okay, so this is kind of a very brief outline of my talk. So I wanted to start with a kind of motivation of why we're interested in heat transports and non-equilibrium heat transport, and also more broadly in quantum thermodynamics. Kind of start with some kind of basic outline of how we theoretically model non-equilibrium transport at a quantum level. Then maybe quickly talk about applications in the context of circuit quantum thermodynamics, and then introduce the more kind of, from a more technical perspective, the types of models that have kind of traditionally or in the last few decades been used to kind of model heat transport in anharmonic nanojunctions. So particularly these types of weak coupling approaches that are quite common, but also kind of looking at more advanced types of methods that are able to treat strong system reservoir interactions. And then towards the latter half of the talk, I'll go more specifically into the types of, into the work that, that is in the paper that I mentioned at the beginning. Okay, so kind of starting with a kind of hopefully gentle introduction. So as I said, this talk is kind of broadly on the topic of quantum thermodynamics. So for those of you who maybe did a physics degree or engineering degree undergraduate, hopefully you learn that, at least learn some kind of macroscopic classical thermodynamics. So macroscopic thermodynamics is a kind of phenomenological theory that's concerned with describing the average behavior of heat, work, and entropy. And so traditionally, this is, you know, focuses on the description of systems that are in equilibrium. So typically their thermodynamic behavior can be described in terms of just a few variables, thermodynamic variables like pressure, temperature, entropy, etc. So what quantum thermodynamics is essentially a kind of extension of the theory of classical macroscopic thermodynamics to essentially any kind of system whose behavior is intrinsically quantum. So think of things which, you know, things like atoms or molecules on a relatively small scale. And so rather than dealing with systems that contain, you know, a large, potentially Avogadro number of particles systems that have much smaller ensemble sizes. And so why is this of interest? Well, you could say from a kind of fundamental perspective, as far as we know that the universe obeys the laws of quantum physics, everything obeys the laws of quantum physics. So if we're going to come up with a universal framework, a thermodynamic framework for the universe, then, well, we might as well make it quantum. But kind of from a more practical point of view, it can potentially, in an analogy to kind of classical thermodynamics, which, you know, from in the Industrial Revolution kind of spawned applications of that theory, kind of spawned, you know, things like motor cars and trains and things like that. Quantum thermodynamics, the interest in quantum thermodynamics is, can we potentially build kind of thermal machines which obey the laws of quantum mechanics, where their behavior intrinsically can be enhanced in comparison to their classical counterparts due to the system exhibiting non-trivial quantum features like coherence and entanglement. So in this diagram here, I just have a kind of a basic example of a heat engine that obeys the laws of kind of classical thermodynamics. So, you know, traditional example is a steam engine. This is kind of, from a purely thermodynamic perspective, this is kind of represented on the right. So essentially, you know, this engine consists of like a hot reservoir and a cold reservoir and some kind of classical working medium. So in this case, this is like the working medium is essentially a gas and a piston, and the gas is either compressed or can expand against this piston. And the kind of the basic principle of how this engine works is that this working medium absorbs heat from a hot reservoir and then expands and pushes against a piston, which performs some kind of work, which is essentially the thing that propels this train forward. And then in that process, you know, in the expansion process, the gas in this container essentially cools and releases heat into a cold reservoir, which is released as steam. So this is kind of a basic idea of how classical macroscopic heat engines work. The idea is that, you know, with applications of quantum thermodynamics, can we kind of miniaturize these types of engines? So rather than having a giant steam engine, can we scale this down to essentially a microscopic scale where our working medium is no longer a kind of a gas and a piston that obeys the classical laws of thermodynamics, but something which is intrinsically quantum? And if this is the case, how does its thermodynamic behavior change? You know, in particular, can we build heat engines that are more efficient than their classical counterparts? Can we build heat engines that maybe have a power output that exceeds their classical counterparts? So this maybe seems something that's more in the realms of science fiction than science, but I wanted to kind of highlight some kind of seminal experimental work that's been done in this field. So I should say that, you know, the field of quantum thermodynamics is a relatively new area. Most of the work in this field so far has been theoretical, although there has been some kind of, you know, some very interesting experimental work that's more kind of proof of principle of this area. So kind of not to go into too much technical detail, but two kind of examples of this that I wanted to highlight was a work that was done in, I think, roughly 2015, 2016, so about 10 years ago, where I think an experimental group at the University of Mainz in Germany basically implemented what you can call a microscopic Otto cycle. So this is essentially a kind of 4-stroke Otto cycle that was implemented using a linear pull trap. So a linear pull trap is essentially, so this is kind of displayed here. So it's essentially you have a single ion that's trapped by radio frequency fields, and in this situation, this single ion plays the role of the working medium. So essentially the role of the gas in the steam engine example that I gave on the previous slide. And so this kind of, you know, in principle works similar to a kind of classical heat engine. You have 4 strokes, you have a heating and a cooling kind of isocores, and then you have 2 isoentropic strokes where the system or work is injected into the system or extracted from the system. So this is kind of schematically displayed here. And so this was, I mean, I think to my knowledge, was one of the first kind of experimental demonstrations of a kind of microscopic heat engine. It's not necessarily a kind of fully fledged quantum heat engine, because the ion in this situation doesn't display any kind of non-trivial quantum features like coherence. So this was kind of more of a, rather than a quantum heat engine, this was more a kind of microscopic classical heat engine. But more recently, there was this experimental work that was done using nitro vacancy sensors in diamond, where they, again, to my knowledge, this is the kind of first experimental demonstration of a fully quantum heat engine, where in some aspects the heat engine can outperform its classical counterpart. So what they did here was they implemented kind of three types of Otto cycles, or sorry, three types of heat engine. So a continuous one, and then a kind of 2-stroke and 4-stroke Otto cycle. And essentially what this work was a proof of principle of a previous theory paper that predicted that in a so-called small action limit, you can implement a heat engine that can produce a higher power output than its corresponding classical counterpart. And so essentially this was the kind of experimental demonstration of or realization of that kind of that previous theoretical work. And so I won't go into the kind of too much of the technical details of this, but if you're interested, then there was this interesting kind of write-up of this. So this was published in PRL. This is a kind of more this is a write-up intended for a more general audience that was published in Physical Reports slightly later. Okay. Yeah, I'm not sure if the people online can hear, but if you speak loudly, I think maybe the people online will be able to hear. Okay.
Can I just announce something? Just what's the axes for this like quantum Otto cycle?
So, and this bit.
Yeah.
So yeah, so the question, if you couldn't hear, was what are the axes? So this is essentially the trap frequency, and this is the mean photon number. So basically, the y-axis is essentially the temperature of the ion, and this is so what? Yeah, this is the trap frequency. So effectively, what the trap frequency does is changing this either essentially performs either an expansion stroke or a kind of compression stroke. So I think if you increase the frequency, you're basically performing a compression stroke. So you're basically injecting work into the system, and you know, the other way around, you're extracting work. Yeah. Okay. Yeah. So that's kind of the more gentle introduction. So this is now getting more into kind of the technical details. So this talk is more specifically about non-equilibrium heat transport. So in those examples that I gave previously, the general setup we have is some kind of quantum system, which could be like our working medium, like that trapped ion that I mentioned. And this system interacts with one or more kind of reservoirs, which we assume to initially be in equilibrium. So how we can theoretically describe this setup is the following. So we have the Hamiltonian of our total system is just the contribution of our system or working medium, plus the Hamiltonians of each of these reservoirs, and plus some component that specifies an interaction between our system S and each of these reservoirs. And so we assume that each of these reservoirs are initially in equilibrium, so they have a fixed temperature and chemical potential. So in this diagram here, we have two bars. One is at some temperature T1, which we assume is greater than T2. And so the initial state can be represented in this way. And so, so we assume that initially each of these bars are internally in equilibrium, but out of equilibrium with each other. Then at some kind of initial time, our system is coupled to each of these reservoirs. And this obviously drives each of these reservoirs out of equilibrium. And then what we're in principle, what we're interested in is looking at both the transient and the steady state regime. So in particular, looking at quantities like the average heat currents between reservoirs and the fluctuations in these heat currents, etc. So these can be represented as expectation values of certain observables, or moments of these observables. And so generally we assume that so our quantum system here is open, and that it is able to exchange energy and and particles of each of these reservoirs, but the kind of the total system, so the quantum system plus each of these reservoirs, we assume to be isolated. And so therefore, according to standard quantum mechanics, so particularly the Schrödinger equation, its time evolution is unitary. So typically it's not possible to describe the time evolution of our entire system, because in principle it contains an infinite number of degrees of freedom, and so therefore it's practically not possible. So what we're interested in doing is being able to extract information on things like these average heat currents and fluctuations, just in terms of what's called the reduced density matrix of our system. So essentially this is some kind of operator. You can think of it as kind of like an extension of a probability distribution that kind of just that allows us to potentially describe things like the average heat flow across our system as a function of time, and also in the asymptotic limit, so as t goes to infinity. Okay, so that's kind of like the generic setup that we're interested in describing. Something that's maybe a little bit more relevant for what I will talk about, what I'll discuss in the remainder of this talk is as follows. So kind of another application of quantum thermodynamics in the context of heat transport is in superconducting circuits. So for those of you who know anything about circuit electrodynamics, know that kind of for the last 20, 30 years or so, superconducting circuits have been kind of one of the most advanced experimental platforms that we have for simulating light matter interactions. So i.e. where you have effectively an artificial atom that interacts with single photons. And so whilst these types of setups are good for simulating electrodynamics, more recently they've been also shown as viable platforms for simulating thermodynamics. So essentially this is kind of what's shown on this slide here. So this is a relatively recent paper where it was an experimental implementation of what's called a heat rectifier or thermal diode. So what this was essentially a heat or thermal rectifier is essentially the kind of the thermal analog of like an electric diode. So an electric diode is essentially an electrical component that allows electrical current to pass in one direction, but is suppressed in the opposite direction. And so what they have here is essentially it's a single transmon qubit that's embedded between two resonators, which here are represented by these harmonic oscillators. And each of these oscillators is coupled to a kind of a copper microstrip, which essentially plays the role of thermal reservoir. So each of these are initially at different temperatures, and they experimentally study the kind of the heat transport across this anharmonic nanojunction. And so this represents a heat or thermal rectifier in the sense of the heat is allowed to flow in one direction, but if you reverse the population distributions for each of these reservoirs, so if you make the cold reservoir the hot reservoir and vice versa, the heat current is suppressed in the opposite direction. So there's kind of inherent asymmetry there, analogously like an electrical diode. And the way that this is manifested is the fact that each of these resonators has a different intrinsic frequency, and this in turn means that the interaction of the transmon qubit to each of these resonators is different. So this kind of asymmetry in the interaction with each of these two resonators produces this kind of rectification effect. And so in these figures, essentially, this figure shows the heat flow across the junction depending on this flux. So the purple and green lines show the difference based on the inversion of these population distributions, and you can see they're not the same. And then this figure here shows the kind of the rectification ratio, which is the ratio between each of these two lines, and they achieve a rectification ratio of about 10% in the setup. And so this is essentially an experimental implementation of this kind of paper here, which to my knowledge was the first kind of work that that gave the most basic setup that allows you to implement a kind of thermal rectifier. So I mentioned that to get this rectification effect, you need this kind of asymmetry in your interaction. But another ingredient that you also need is that your junction needs to be anharmonic. So if you try to do something similar with a purely harmonic system, this rectification effect doesn't work. And so this paper just essentially proposed a basic model for a rectifier in which this system is anharmonic, so a two-level system. Okay, so this kind of basic setup I mentioned, this is referred to where you have a two-level system. So in the previous diagram, this was a transmon qubit that interacts with two thermal reservoirs. This, for those of you who know anything about open quantum systems, this is known kind of generally as the non-equilibrium spin-boson model. And so theoretically, how we describe the setup, which is outlined in this paper here, is as follows. So you basically have the Hamiltonian of the total system is given here. So you have a two-level system with some kind of energy splitting delta. This interacts with a hot reservoir and a cold reservoir, which are initially assumed to be in thermal equilibrium. We assume our system interacts with each of these reservoirs with the same interaction operator, which here is the Pauli Z. And we assume that each of these reservoirs comprises essentially an infinite collection of non-interacting bosons. And we assume that each of these, the interaction between our two-level system and each of these reservoirs is linear in the sense that this interaction operator is just a linear combination of bosonic creation and annihilation operators. Okay, so I kind of mentioned a little bit earlier that we're interested in this type of setup. We're interested in being able to describe things like the heat current across the junction, both in the transient and steady state regime. And so this generally involves solving for this reduced density matrix object that I mentioned. And so a kind of very common approach for treating these types of systems or treating the heat currents in these types of systems is using a so-called second order master equation approach. So the idea behind this approach is that if you assume that our junction or our two-level system interacts weakly with each of these two reservoirs, so if we assume that the interaction for simplicity is the same between these reservoirs, so here lambda, this parameter lambda sets the interaction strength. If we assume that lambda 1 is equal to lambda 2, and we assume that generally this is much smaller than the frequent or the energy scales of our system, then we can apply the second order master equation to describe the heat current across this junction. And so essentially this master equation is an equation of motion for the reduced density matrix of our system, and it has this kind of structure. And so our first term is a kind of unitary term that depends on this system Hamiltonian, and then our second term describes essentially the dissipative effects on the system due to its interaction with each of the reservoirs. And so within this kind of weak coupling framework, which is valid to second order in this parameter lambda, we're able to devise essentially thermodynamic laws in this setup. So in particular, we can write down a first law, which is essentially just a statement of energy conservation. So this just tells you that in particular in the steady state, that any energy that is absorbed by the system is equivalently emitted by the system into the cold reservoir. And so the first law here relies on this definition of heat current. So it depends on each of these dissipators. So crucially, the fact that these dissipators are local to each of these reservoirs, so they just depend on this index J, means that we can kind of unambiguously identify heat currents in this way. And with this definition of heat current, we can also write down a second law, which essentially tells us that the rate of entropy production is non-negative. Okay, so this tells us that this kind of second order master equation approach for describing the heat currents is consistent with kind of the first and second law of thermodynamics. Okay, so traditionally, we also kind of assume that these reservoirs are structureless in the sense of that the interaction between the system and each reservoir is characterized by what's called an ohmic spectral density. So this spectral density quantity is essentially a function that describes how our system interacts with each of these reservoirs at a particular mode frequency in the reservoirs. And typically, we assume that these spectral densities are ohmic in the sense of the lower frequency the lower frequency end of the reservoir dominates the interaction. And so this is assumed to be basically linear in this frequency. And in this type of situation, so you assume that the small frequencies, that each of these spectral densities have a kind of linear scaling in omega. You also assume that this spectral density tends to decay up or to be kind of cut off at high frequencies. If you assume that this cutoff, these functions decay sufficiently fast, then this enables you to apply this type of second order master equations that I gave on the previous slide. And so in this framework, this weak coupling framework in which we can apply these master equations, you can derive an expression for the steady state heat current for this model. And it has this expression here. So this is what's derived essentially in this paper. And the thing to note about this expression, well, I should say that it depends on the spectral densities of each of these reservoirs, but it depends on the so these ends here are just the Bose-Einstein distributions of each of the reservoirs. So it just gives us the population distribution of each of the reservoirs at a particular temperature. And what's notable about this expression is that it's asymmetric in each of these labels I and J. So if we assume that our system has a different interaction with each of these reservoirs, then if we invert these population distributions, if N1 goes to N2 and vice versa, then the heat current changes. So this is essentially this rectification effect that I mentioned slightly earlier. Okay, so this is a kind of well-known weak coupling framework that's been traditionally applied to study non-equilibrium heat transport in this non-equilibrium spin-boson model. There's also been kind of extensions of this type of framework to deal with situations in which in situations where this interaction is weak. So basically where this master equation approach is no longer appropriate. And so I won't go into too much details, but this is just kind of the highlight these other approaches. So these consist of the so-called non-equilibrium Green's functions approach, a so-called reaction coordinate mapping, and this hierarchical equations of motion. So I'll talk a little bit more about these hierarchical equations of motion later on when I go into a bit more of the details of the paper. So the work that I did last year. Okay, so this is just to mention that there are alternative kind of frameworks for treating strong interactions. And so a situation where it's kind of necessary to move beyond this second order master equation approach is the following. So a variant of this non-equilibrium spin-boson model that's kind of been proposed in the last few years is one in which you still have this configuration where you have a two-level system that interacts with a hot and a cold reservoir, but you now assume that the system coupling operators to each of these reservoirs are no longer necessarily the same. So in the previous example, these were both, for example, the Pauli Z operators. But now what you do is you replace one of these operators with something more general. And so this is parameterized in terms of this argument theta2. And so essentially we recover the previous model if theta is, I guess, pi over 2. And kind of this seems like a relatively simple change, but it has kind of quite drastic consequences for the characteristics of the heat transport. So this is what I'll discuss now. So what you can show is that you can basically derive using the Heisenberg equations of motion, you can derive an expression for this steady state heat current, which depends on the system Hamiltonian and the interaction Hamiltonians between the system and each of these reservoirs. And it has this kind of generic structure. So in the previous model that I discussed, the basic one, where these operators are the same, you essentially only have a single contribution to this steady state heat current that stems from this first term that's highlighted in red. And so this represents what's called a system Barth transport pathway, which I'll explain just now. And so what happens is that if you change this operator in such a way that the interaction operators no longer commute, you get basically the activation of a kind of second transport pathway, which is represented by this green term. And so this is what's referred to as a Barth transport pathway. So it basically represents a type of heat transport that is qualitatively different than the heat transport that's described by this red term. And so you can kind of see that trivially, if these system interaction operators commute, then this second term disappears. So it only happens in situations where you have this kind of intrinsically non-commutativity between these interaction operators. And so this type of situation was explored in these two papers, one which appeared on the archive only a few weeks ago. In this paper, what they show here is essentially these two figures illustrate the characteristics of the heat transport that depends on these two different pathways. So in this figure A here, this alpha parameter here is essentially the lambda parameter that I introduced in the previous slide. So it essentially modulates the interaction strength with each of the reservoirs. And this axis shows the average heat current in the steady state regime. And so in the basic model that I showed on the previous slide, where these two operators commute, you can show that the steady state heat current exhibits essentially a quadratic scaling in this parameter in the system reservoir interaction strength, lambda. And so that's represented by this kind of red line. But if you then kind of perform this kind of rotation with respect to this parameter alpha 2 in such a way that this green interaction operator no longer commutes with this operator Pauli Z, then you produce a totally different scaling in this steady state heat current. So in this case, you get actually a quartic scaling. So rather than being quadratic, it becomes quartic. And the way that so I mentioned these two terms, system bath transport pathway and bath transport pathway. So you can kind of understand this in the following sense. So in the situation where you have commutative operators, so where you only have this term present, you can show that if this energy splitting becomes very, very small, so essentially in the limit that delta goes to 0, you can show that according to this red line here, that the heat current basically also decays to 0, which is naturally what you would expect, since if you compress the energy levels, the system can't basically absorb any excitations from the hot reservoir, so it basically shuts off the heat transport. But interestingly, when you activate this alternative bath transport pathway, what happens is that when this is dominant, when you decrease this energy splitting, the heat current actually remains completely invariant. So it kind of scales off and just goes flat. And so this represents a bath transport in the sense of the system mediates the transfer of excitations between the hot and the cold reservoir, but it doesn't actually become excited in the process. And so that was quite interesting kind of variant of this kind of basic model that I showed previously. And so now in like the remaining 20-15 minutes or so, I'll talk more specifically about some of the work that I did, which was kind of motivated from these types of variants of the basic non-equilibrium spin-boson model. So kind of going back to this kind of experimental setup I talked about, which was this kind of thermal rectifier. This was based on having a two-level system embedded between essentially two harmonic oscillators, which then in turn interact with two kind of mesoscopic thermal reservoirs. So in this paper, what we studied was a similar situation to this, but one where you kind of add additional structure to each of these two reservoirs. So in particular, what we do is assume that rather than each of these, so the hot and the cold reservoir being comprised of a single oscillator plus an additional heat bath, we add an additional harmonic oscillator into the mix. And so it has this kind of alternative kind of structured configuration where I should say that so this kind of these two oscillators in this setup here now interact with an additional oscillator, which is itself isolated from any thermal reservoir. And so this aspect is quite important, and we assume they have there's some parameter that modulates this interaction that we assume is generally much smaller than the resonator or like the natural frequencies of these oscillators. And so we have this kind of we have a similar type of Hamiltonian to the previous models that I mentioned, except now this kind of the bath Hamiltonian now has this kind of new intrinsic structure, which reflects essentially what's represented in this diagram. And what I'll go on to show is that you could say, okay, why are you interested in this particular setup? It seems very particular. But what I'll go on to show is that adding this additional oscillator into the reservoirs can produce similar types of scaling effects to what I showed in the previous slide, where you have this kind of, instead of having a quadratic scaling in the asymptotically weak coupling limit, you have a quartic scaling. So you can kind of use this kind of like reservoir engineering to produce these alternative types of heat transport characteristics, like you can if you change the coupling, the properties of the system environment coupling operator. Okay, so so I mentioned previously that the interaction between the system and each of these reservoirs can be characterized in terms of this quantity that's known as the spectral density. And so from an intuitive point of view, how you can see a way to see how adding this additional harmonic oscillator into each of these two reservoirs changes the characteristics of the interaction between the system and each of these reservoirs is as follows. So in this diagram here, what it depicts is the spectral density corresponding to essentially this setup, where you only have a single oscillator in each reservoir. And so that's given by this kind of green line here. So here, okay, it represents what's in this diagram, but here I give it the acronym ungapped non-equilibrium spin-boson model. And what you can show is that if you add this additional oscillator, so what we considered is that it produces this kind of interesting phenomenon where if the frequencies of each of these two oscillators are the same, what happens is that you produce this kind of gap in the spectral density, in the sense of there's a point on the domain of this function where it basically is identically zero. And as I go on to show, this has a kind of drastic impact on the heat transport characteristics. So specifically in terms of the scaling with respect to the interaction strength. And what's interesting is that this so whilst you can apply in the weak coupling regime, you can apply a master equation approach to this type of model here. But when you add this additional oscillator, even if the interaction strength is very, very weak, it still produces an incorrect result. So basically, if you introduce this extra structure into the reservoir, the second order master equation approach becomes invalid even in the asymptotically weak coupling regime. And so in order to actually treat the heat currents in this type of system, we have to rely on a different approach. And so the approach that we used was this so-called hierarchical equations of motion. And so this is a approach which is valid beyond second order in the system reservoir interaction strength. I won't dwell too much on the technical details, but this is just in case people are interested. So this hierarchical equations of motion approach is kind of like an extension of a master equation approach, in the sense that rather than just having an equation of motion for the reduced density matrix of your system, you extend this to a kind of hierarchy of equations that depend on these objects that are called auxiliary density operators. And they obey this equation here. Okay, it's a little bit complicated, but essentially the idea is that you have an equation of motion for your reduced density matrix from which you can extract information about the heat currents and fluctuations in these currents. But this reduced density operator couples to other kind of effective density operators that, in a sense, encode information about system reservoir correlations and higher than second order effects. And so by basically solving these equations, you can then, extract information, as I said, extract information on heat currents and things like that. What's interesting also about this framework is that it also allows you to extract information, not just in terms of the reduced system density matrix, but also in terms of these auxiliary density operators that's kind of represented in these two equations here. And so what this expression here is essentially just an analytic expression for the steady state heat current, written in terms of a number of these auxiliary density operators. And the second equation is the kind of the noise, so the second order moment of this heat current operator. And this noise kind of has a kind of a contribution that kind of represents the thermal fluctuations that are there in equilibrium. So this depends on essentially the correlation function of one of the reservoirs at t=0 plus some additional term that kind of characterizes the noise out of equilibrium, which you can evaluate in terms of these auxiliary density operators. Okay, so using this approach, we kind of studied the heat transport characteristics in this kind of what I call this gapped equilibrium spin boson model, so the one where we have this additional harmonic oscillator present. And so what's kind of first talking about the transient regime. So this is what we look at is the time dependence of the heat currents, is that you can, interestingly, if the interaction strength is relatively strong, what you find is that adding this additional harmonic oscillator doesn't really affect the transient properties of the heat current. So in figure A, you basically have the heat current corresponding to the model where you only have a single oscillator present in each reservoir. And figure B shows the case where you have this additional harmonic oscillator. And you can kind of qualitatively see that they display a relatively similar behavior. The interesting behavior occurs in the asymptotically weak coupling limit. So basically, as you take the limit that lambda goes to 0, or at least becomes much smaller than the energy scale of the system. And so this next figure here shows the same, but effectively in this limit. And so you can see now qualitatively, you have this quite different behavior. So the first figure here is the plot of the case with the structured reservoirs with the additional oscillator, and then the second figure is the one without the additional oscillator. So you can see that compared to the first case, they have there's a qualitatively different behavior. So this is the kind of the transient behavior. You can also see a drastic difference in the steady state regime. So what this first figure shows is the scaling in the heat current as a function of this of the interaction strength on a logarithmic scale. And you can see that in the asymptotically weak coupling limit, you get something similar to what I described with this extended non-equilibrium spin boson model, where you have non-commuting interaction operators. So you can see that basically this additional oscillator here produces this quartic scaling now. So as you decrease the coupling strength, the steady state heat current now no longer scales quadratically, it scales quartically. And you can see its magnitude is significantly, as a consequence of this, it also significantly suppresses the heat current. Interestingly, if you look at the noise, if you kind of look at the fluctuations in this current, they actually show almost no difference. So both of them scale quadratically in the coupling strength, which is consistent with the fluctuation-dissipation theorem. You can also look at the behavior of these heat currents as a function of the temperature difference between the two reservoirs. So what is also perhaps interesting is that from using linear response theory, you can show that if these two reservoirs are only slightly out of equilibrium with each other, so if this temperature difference, so this delta T here is just the difference in the temperatures of the two reservoirs. If this temperature difference is small, you expect the steady state heat current to obey Fourier's law, which essentially tells you that this steady state heat current should scale linearly in the temperature difference if delta T is small. So far from equilibrium, when where delta T is large, you don't expect this to hold. And so this is what you find with this ungapped model, where you don't have this additional harmonic oscillator. But interestingly, in the weak coupling limit, we find that even in the regime where delta T becomes can become quite large, the heat current still obeys Fourier's law, even quite far from the away from the linear response regime, which I wasn't exactly sure how to interpret this, but is potentially interesting. And yeah, I think that's more or less the end of the talk. So I think I have only like 5 minutes or so left. So yeah, so just a kind of very basic conclusion. So what our work in particular illustrated is, well, our work was intended to be a kind of extension of these previous variants of this non-equilibrium spin boson model, which show that you can produce you can produce a drastic change in the steady state heat transport characteristics of anharmonic nanojunctions by changing the properties of the system reservoir interaction. What we did was kind of build on this work to show that if you can also kind of engineer these reservoirs in a similar way to reduce this different heat these different heat transport characteristics. We also get this interesting behavior where these in the weak coupling limit the steady state heat current obeys Fourier or even far from equilibrium. What would be interesting, so an extension of this work could be to look at how introducing this additional structure into the reservoirs can affect the rectification behavior. So as I mentioned, if you change the population distributions of the reservoirs, you can produce an asymmetric change in the heat current. So is this rectification enhanced with this additional structure in the reservoir? That could be something to look at. And there could also be other applications to other types of thermal devices, so heat engines, which I mentioned at the beginning of the talk. So if you're interested in looking at this work in further detail, then this is the corresponding reference. And yeah, just to say, I included a picture. It's maybe unnecessary to include a picture of Francesco, but just to say this work was done in collaboration with Professor Francesco Petriccioni, and also just to acknowledge some helpful kind of comments from collaborators. And yeah, so let me just finish there by saying thanks for listening. And yeah, if you're interested in any of the work that our group does here in Stellenbosch, then please check out this website. Okay, thank you.
Yeah, Graeme, thank you very much. Questions for Graeme?
Do you want to unmute yourself?
Yeah, I've done it. So thank you. Are there questions for Graeme? Comments? Don't be scared. For you, everything is new. So you should have lots of questions. Matt.
This question, but in the other work that showed a different kind of scaling, reported scaling, they have that producing like the difference in operator strengths or like the different operator. But in yours, you get a quantity scaling, but just doing the couple of harmonic oscillators. So your couplings are identical.
Yeah.
You change one of the couplings, you get it. You get a different scaling, or I mean, so the way that they change their coupling.
You mean like with it? Yeah, so you would get the same thing, but the scaling would be the same because let me maybe just repeat that to people online, because I'm not sure if they heard the question. So I think the question was in the type of model that we studied, if you would also introduce these, let me go back to that, Antonio. Yeah, so sorry. Yeah, so in this type of model we studied, we assume these kind of commuting interaction operators. If you also introduce non-commuting interaction operators, would that also affect
yeah.
Is that yeah? So it wouldn't, but that's just because adding this additional oscillator already produces a quartic scaling. So if they were non-commuting, you would get this quartic scaling, but it would, yeah, I'm trying to think of the best way to explain it. Like, as long as you didn't have, okay, let me say this. So the reason you get this quartic scaling in our model is because you assume that this energy gap in the system, this delta parameter, matches the oscillator frequency of these oscillators in each of the reservoir. And the consequence of that is that you can show that this shuts off like the transport pathway, which scales quadratically in this parameter lambda. So the next leading order effect is quartic. So that's why you get this quartic scaling. If you made the interaction operators non-commutative, as long as this quadratic term was still zero based on this property of matching delta to the frequency of the oscillators, you would still get a quartic scaling that wouldn't affect it. If you change the operators such that it would no longer be zero, then obviously it would become quadratic, because that would be the lowest order or the leading order effect that would affect the transport characteristics. If that makes sense.
Another question?
Yeah.
Emmy?
The result, like that was funny in the beginning before about the fact that you can get like heat transport that's direct. It seems like it's directly from one path to the other.
Yeah.
Yeah. Can you see from your results if you get something like that happening as well?
We don't. So this is it's purely a feature of this non-commutativity. So in our model, because we have commuting operators, you don't have this path transport pathway. It's purely system path. So kind of we get the same scaling as them, but it's the mechanism behind the scaling is the same as the system path transport pathway. Whereas in this model, the scaling is attributed to a different type of mechanism.
Yeah, but
Yeah.
I mean, intuitively, then it's like, yes, something strange is happening where the bath and the two baths can exchange stuff, but without the subsystem. Whereas you have additional systems that seem to allow this.
I'm not sure this is a good way to think about it. It's probably wrong, but I like to think about it in terms of virtual particles, where you kind of have like the creation. You can have like particles which mediate certain processes, like in kind of particle physics. I mean, I'm not a particle physicist, so this may be really wrong if anybody else is a particle physicist. But like you have these virtual particles that can mediate certain processes, but aren't kind of directly involved. But like, so this is maybe something similar. I don't know, like where you, yeah. But I'm not. Yeah, I'm not a particle physicist. So. Yeah. I think also interestingly, it's well, I would say it's an intrinsically quantum feature because it depends on this new non-commutativity property. So this is obviously something which is intrinsically quantum. So my assumption is that it can't happen classically.
Yeah. I wonder if you could measure that experimentally, like you could measure that okay, the heat was transported by this interaction or that one. I mean, I don't know.
Yeah.
None of us are experimentalists, I guess, but that would be cool if that was possible.
Yeah, I'm assuming it's possible to do experiments.
And the interesting thing that I learned earlier this week, probably yesterday or 2 days ago, there is an engineering, a group that designs QUITs and tests them. Yeah, and they also develop software that even IBM uses when they build quantum computers. So we should really get in touch with them because they might be interested for, heat issues. Yeah? But on another note, this is motivated mainly by nanotechnology, squids and so on. Is there any mechanism that we could, any chance that we could make use of something like that in a biological context? We also, I don't know, I have no idea. We're also full of nanomachines. Huh?
The introduction part that Graeme mentioned, that part is exactly what we usually start our talk, use coherence and for functional and quantum thermodynamics, we want to use coherence, but I haven't seen the entanglement or something quite. You mentioned
no, there's no. In the setup that we consider, I guess you could say this. Well, it's done within a quantum framework, but it's not. There's nothing, I guess you say, inherently quantum about it. Yeah, so it's the behavior that we see isn't to do with kind of coherence or as far as I'm aware, it's to do with kind of non-trivial quantum effects.
Yeah, but the model is more or less similar.
Yeah, so maybe there is something that can be transferred.
Yeah. I'm also recently interested to if we use different. You use what kind of environment do you use? Open. This paper.
You mean like the structure of the Hamiltonian?
No, the spectrum.
Spectrum.
But okay, the interaction between these components. So this part is ohmic.
Okay.
So it matches. So this kind of represents an extension of the basic non-equilibrium spin-boson in the model in the sense of your system interacts with an ohmic reservoir, but it's now mediated through this kind of new interface, which is like these additional oscillators. So you still have an ohmic reservoir, but yeah, you have these other oscillators, and that's what produces this different, gapped effect. So specifically this configuration in the interaction between the oscillators and the system that produces this kind of blue curve, which has this gap in its spectrum. You mean if this is no longer ohmic? I'm not 100% sure. Well, I would say that, okay, the reason I assume them to be ohmic is because it complies with the previous the basic model where you usually assume ohmic spectral densities. But also I assume them to be ohmic because in that case, you can show that it's possible to derive an analytic expression for this spectral density, which makes it easier to see this type of gap feature. If you change this to be no longer ohmic, I'm not sure you could derive an analytic expression. You might be able to, but I don't know. Or I would also expect it to kind of completely change you may no longer have this gap feature. I don't know, but yeah.
The paper you drive.
Yeah. So I haven't written this expression here, but you can, if you look in the paper, there is an expression for the spectral density.
Okay, there's a question online, please. Abdul, you can just unmute yourself and ask. Sorry.
On the beginning of the slides, where you have this diagram of representing the system and interacting with the two baths, the bath at the hot reservoir and the cold reservoir. So the model is like, since my understanding is you are trying to study the heat transport between the hot reservoir and the cold reservoir. And then those systems, are they interacting, the quantum systems, are they interacting with, are they coupled to both the hot reservoir and cold reservoir, or there is a medium between, it's only some systems are allowed to interact with the hot reservoir, while some are allowed to interact with the cold reservoir?
Yeah, so if I understood your question correctly, yeah. So in this schematic here, this R1, R2, etc. Each of these are thermal reservoir.
Okay.
You also assume collectively that these reservoirs with these oscillators, which here I call B1 and B2, they themselves form reservoirs in the sense of at some initial time, we assume them to collectively be in equilibrium. So at some temperature, which matches the temperature of this other reservoir.
Okay. And then the systems here in between lambda 1 and lambda 2, they are quantum systems. And then, so each of these interact with both bath 1 and bath 2 at the same time?
Yeah, it's just, yeah.
Okay. Okay, good.
I mean, you could consider more, one of the applications that I mentioned was to kind of heat engines. One extension of this model could be to look at the case where these interactions are time dependent. So you could switch off the interaction with the one reservoir, turn it on at different times, and that could be used in a heat engine. But in this case, it was just the same interaction between both of the reservoirs, and it's a simultaneous interaction, yeah.
Wow. So just recently, like this week, we started a project that tries to model spin systems, like in semiconductors, spin systems that interact with this kind of thing. But in our case, we wanted to study the heat transport from the hot reservoir to the cold reservoir, where you have the spins in a linear chain, and then you have a source and a sink. So we wanted to model entanglement dynamics, and then this thing is pretty similar. Like we can infer many ideas from these things. In fact, this is like the main reason I joined this talk today.
Yeah. So in this
I
case,
would
So in this case, the model that you described is somewhat similar, but in our case, we just have a single spin.
Okay. Yes. Okay. So I would like to be in touch, maybe, so to grab some ideas. Is this slide going to be online somewhere, or?
Sure, I can, I don't know whether it's possible to put on the NETheCS
Yeah,
site,
yeah,
or
we can do that.
you can also email it to you. if
Yeah,
you
we can
like.
put them on the NETheCS website and even on our quantum website. Yeah, and the recording will be in our YouTube channel. Yeah, but
Okay.
we would be interested. Why don't you give us a talk one of these Fridays?
Yes, why not? This is something very new to me, but I'm trying to. My main background is purely in condensed matter, but this is what we are trying to start exploring these days. I am a postdoc in Trieste, Italy, working with the Baroni's group, Stefano Baroni, the group that develops the quantum espresso software.
Yeah, I know him. Yeah.
Yes, and I did my PhD in South Africa actually, and I was part of your school in 2019 that took place in Drakensberg, I think in KZN.
Excellent.
Yeah.
Then
So
just send us the title and the abstract, and we invite you one of these Fridays to give us a talk.
Okay, so how do I write to you?
I can put my email in the chat. Sorry.
Okay.
Voila. Here we go.
Great, thank you.
Excellent. Thank you very much. Then
Yeah, thank you.
people are leaving online and in person. So let's call it a day. Yeah. So thank you very much, Graeme, for the very nice talk, and thank you for all of you here and in the cloud. And we'll make a plan for next week. Yeah. Thank you.